Hello students, in this lecture let us solve few numerical on conductivity of metals and semiconductors. See the numerical statement. Calculate the conductivity of germanium specimen. So this is a numerical on conductivity of germanium. If the donor impurity is added, what does this mean? This is a conductivity of N type of germanium specimen. If the donor impurity is added to the extent of 1 part in 10 raised to 8 germanium atoms at room temperature. So see, this sentence gives us the concentration of donor impurity. What is concentration of donor impurity? 1 part in 10 raised to 8 germanium atoms. So we need to calculate number of germanium atoms in 1 cc, 1 centimeter cube, and if we divide it by 10 raised to 8, then we will get the concentration of donor impurity. The data given is Avogadro number, number of atoms per mole, atomic weight of germanium, density of germanium is given. We will need it because we want to calculate number of germanium atoms per cc, and mobility of electron is given. It is n type of semiconductor. Mobility of electron is required. It is 3800 centimeter square per volt second. So let us see the solution. So what we need to calculate? We need to calculate the conductivity. So what is the formula for conductivity? It is sigma n equal to nd mu e e. It is n-type semiconductor. So mu e is given. E is also known, which is charge of electron. We need to calculate nd, which is concentration of donor impurity. So, to calculate this concentration of donor impurity, what is 1 mole of germanium? 1 mole of germanium is 72.6 grams. So, 72.6 grams of germanium contain Avogadro number of atoms. So, how many atoms will be there in 5.32 grams? 5.32 is density of germanium. So if we calculate this, we will get the number of germanium atoms in 1 centimeter cube because it is density of germanium. So doing this calculation, we will get 5.32 grams of germanium contain 4.41 into 10 raised to 22 atoms per cc. So what we need to do to calculate the donor impurity concentration, we need to divide this by 10 raised to 8. So the donor concentration comes out to be 4.41 into 10 raised to 14 atoms per centimeter cube. So now we know everything in this formula. ND we have calculated using Avogadro number. Mu E, which is mobility, it is given. E is the charge of electron. Now we can put the values as shown in this step. We have put the values and we can calculate the conductivity of this germanium specimen to be equal to 0.268 mho per centimeter. See the numerical statement. Calculate the conductivity of pure silicon at room temperature. This means the numerical is on conductivity of intrinsic semiconductor. When the concentration of carrier means concentration of electrons in the conduction band as well as concentration of holes in the valence band. Being an intrinsic semiconductor, concentration of electrons in the conduction band is equal to concentration of holes in the valence band. So this concentration of carriers is 1.5 into 10 raised to 16 per meter cube, and mobilities of these charge carriers are also given. Mobility of electron is 0.12 meter square per volt second, and mobility of hole is 0.05 meter square per volt second. So this is the data given what we have written. Again, this is concentration of carriers, that is concentration of electrons and holes. Those are equal because the semiconductor is intrinsic. Mu E is given and mu P is given. We need to calculate conductivity of this intrinsic semiconductor. Let us solve it. The formula for conductivity, sigma I, is Ni into E in bracket mu E plus mu P. We need to do nothing but only to put values and calculate the answer. So these values are put here and we will arrive at the answer. Sigma I is equal to 4.1 into 10 raised to minus 4 mho per meter. See the numerical statement. The resistivity of N-type semiconductor is 10 raised to minus 6 ohm centimeter. Calculate the number of donor atoms to obtain this resistivity. So this is N-type semiconductor. Resistivity is given. We need to calculate donor atoms to be added. Donor concentration we need to calculate. Mobility of electrons will be required because it is N-type. 1000 centimeter per volt second. So this is again the given data is summarized here. Resistivity is given, mobility of electron is given. We need to calculate donor concentration. Let us solve the numerical. Let us write the formula for resistivity. Resistivity is equal to 1 upon Nd mu E because it is N-type semiconductor. We need to calculate the concentration of donor impurity, so we will rearrange this equation for Nd. And what is the else thing we need to do? We only have to put the values which are given here and we can arrive at the answer as shown. 6.25 into 10 raised to 21 atoms per centimeter cube. Let us see the next numerical. Calculate the conductivity of pure silicon. Means again the semiconductor is intrinsic. Pure silicon at room temperature when concentration of charge carriers is given 1.6 into 10 raised to 10 per centimeter cube. So being an intrinsic semiconductor, we will need mobilities of both electrons as well as holes, which are given to be 1500 centimeter square per volt second and 500 centimeter square per volt second. So here again the given data is summarized. Concentration of electrons and holes which will be equal because the semiconductor is intrinsic semiconductor. It is 1.6 into 10 raised to 10 per centimeter cube. Mobilities of electrons and holes are given as shown. What we need to calculate? Conductivity of intrinsic silicon. So let us solve. Let us write the formula Ni into E in bracket mu E plus mu P. We need to do nothing but to put the values which are given, and we will do the calculations to arrive at the answer. Sigma intrinsic is equal to 5.12 into 10 raised to minus 6 mho per centimeter. Let us see the next numerical. Calculate the conductivity of extrinsic silicon at room temperature. If the donor impurity is added in 1 in 10 raised to 8 silicon atoms. Here, the concentration of silicon atoms is directly given 5 into 10 raised to 22 atoms per centimeter cube. This is directly given, otherwise we would have to calculate it using Avogadro number and density of silicon as we have done it in the earlier numerical. But now here the concentration of silicon atoms is directly given. The mobility of electrons will be required 1300 centimeter square per volt second. Given data is summarized here. Number of silicon atoms per unit volume is given. Mobility of electrons is given. We need to calculate conductivity. Let us solve the numerical. Sigma n is equal to nd mu e. So nd will be equal to concentration of silicon atoms divided by 10 raised to 8. So concentration of silicon atoms is 5 into 10 raised to 22 divided by 10 raised to 8. So concentration of donor impurity will be 5 into 10 raised to 14 per centimeter cube. So only now we need to put the values in this formula. Nd we have calculated, mu E is given, E is known. So we will put all these values to get the answer 0.104 mho per centimeter. Let us see the next numerical. Find the resistivity of copper if each atom of copper contributes one free electron for conduction. So what this first sentence gives us, it says that number of free electrons per unit volume is equal to number of copper atoms per unit volume, because each atom is contributing one free electron for conduction. So if we have to calculate number of free electrons per unit volume, we need to calculate number of copper atoms per unit volume. So if we need to calculate number of copper atoms per unit volume, then we will need atomic weight of copper, Avogadro number, density of copper. To calculate the resistivity, also we will need mobility of electrons, which is given here, 43.28 centimeter square per volt second. Let us summarize the given data. Mobility is given, density is given, atomic weight of copper is given. It is said that there is one electron per atom. Avogadro number is given. Let us solve the numerical now. We need to calculate the number of copper atoms per unit volume. So, because we need to calculate number of charge carriers, that is electrons, number of electrons per unit volume. So, to calculate this, what we will need? 1 mole of copper. What is 1 mole of copper? It is 63.5 grams, because 63.5 gram is atomic weight of copper. So 63.5 gram of copper, that is 1 mole of copper, contains Avogadro number of atoms. 8.96 gram of copper contain how many number of atoms? 8.96 gram is density of copper. So calculating this, we will come to know that there are 8.494 into 10 raised to 22 atoms per cc. Same will be equal to number of free electrons per cc because each atom is contributing one free electron for conduction. So in this way, we have calculated the concentration of charge carriers, that is concentration of electrons in copper. Now we can write the formula for resistivity. Resistivity is equal to 1 upon Ne mu E. So Ne we have calculated, mu E is given to us, E which is charge of electron is known to us. Now we only have to put the values here. So the values are put here in the formula and we will calculate resistivity to be equal to 1.7 into 10 raised to minus 6 ohm centimeter. So the answer for resistivity we have calculated here. Let us see the next numerical. Calculate the energy band gap in germanium. It is given that it is transparent to radiation of wavelength greater than 1700-760 angstroms. So the wavelength of light should be greater than this 17760 angstrom units. So what is the given data? Lambda is 17760 angstroms. Planck's constant is known to us. Velocity of light is known to us. Let us solve the numerical. What is the formula which will be required? Absorption begins when the energy of photon is minimum equal to energy band gap. So this Eg, which is energy gap, it should be equal to the energy of photon, minimum energy, which is photon. So Eg is equal to h mu, which is equal to hc upon lambda. So what we need to do is only to put the values which are given. This formula will give us energy gap in joules because all quantities we have taken in SI units. So doing the calculations, we will arrive at energy gap is equal to 1.12 into 10 raised to minus 19 joules. But if it is asked in electron volts, the conversion of electron volts is required. So this energy gap comes out to be equal to 0.7 electron volts. We are dividing by 1.6 into 10 raised to minus 19 because we are converting energy gap from joules to electron volts. So the answer is 0.7 electron volts. Let us see the next numerical. Calculate the band gap energy in silicon. Given that it is transparent to radiation of wavelength greater than 11,000 angstrom. The numerical is exactly similar to the earlier. Earlier was germanium, now here it is silicon. See that the wavelength is changed and nothing else. So this is a given data which is summarized. Lambda is given 11,000 angstroms, Planck's constant and velocity of light is known to us. Let us solve the numerical. The energy of photon should be minimum equal to the energy band gap for the given semiconductor. So this Eg will be equal to h mu, which is energy of photon, so which is equal to hc upon lambda. We are putting the values. Eg is equal to Planck's constant, velocity of light, and lambda which is given. We will put in the formula and simply we will calculate the answer. This formula will give us the answer in joules, because all quantities which we have taken, those are in SI units. If the numerical is asking us energy gap in electron volts, then we need to convert this energy gap into electron volts. For that, we need to divide it by 1.6 into 10 raised to minus 19. This gives us the energy gap for the given semiconductor is 1.129, or approximately it is 1.13 electron volts. Thanks a lot, students. This video will help you. I hope this video will help you to solve the similar numericals on conductivity or resistivity of metals and semiconductors. Thank you.